Okay, well, welcome to everybody. Now, those of you who have attended these events in the past will know that 2025 marks the 10th anniversary of Brain and Mind. Over the past 10 years, we've covered a vast array of topics which have included addiction in the brain, art, music, perception, and so many more. Do the maths, it's about 30. Interdisciplinary work is really important, and some might say the way of future research. It is the belief of those behind Brain and Mind that interdisciplinary work is best engaged in by those who have a strong grounding in their own chosen fields of study. With this in mind, we don't ask our speakers to fit in with each other's talks. Rather, we just ask each speaker to tell us about how his or her discipline investigates the topic that we've chosen for discussion. We find that this produces a strong springboard for interdisciplinary thought and research. The very first step in all this, I believe, is respect for what each discipline is able to bring to the table. What I hope our students, both those already engaged in research and more generally, will take from these events is a sense of how complex, how multidimensional the topics we bring for discussion are, and how much we have to learn from each of the disciplines that are represented. Now, we also invite A-level students amongst our audience, and I wonder, are there any here tonight? Usually oh, excellent, thank you so much. Welcome especially to you, because we really want you to see where your future research may go. And for those of you who haven't attended before, I should explain that we have been for a few years now collaborating with the medical school in Hamburg, where one of our founding members, Professor Micah Glitch, is now teaching. Now, the audience is usually up on the screen, but tonight they have a big event in Hamburg and decided they would prefer just to be the non-visual partner, but they will come in with questions if they have any, and I'll take questions both from Hamburg and from the audience here in Oxford. And I'd like to thank the Medical School Hamburg for their continued support for this event, as well as St. Hilda's College. Now, I mentioned that one of the topics we covered over the past 10 years is art and the brain. And some of you may have noticed, although I think some came in rather quickly, that there is currently running in the foyer of this building an art exhibition, paintings by the artist Lynn Cameron, who's here tonight. And indeed, there's information about the event that's out in the foyer in tonight's program. So on the back page, you can see. And not only is the exhibition running for the next about 10 days, but it's also, there'll be another interdisciplinary event on the 17th of February called Connecting Conversations. And this will bring together the artist herself, as well as an applied linguist, a poet, and a philosopher, me, to discuss Lynn's work in connection with their own disciplines. It should be a fascinating evening or afternoon, and you're all welcome to attend and to tell your friends about it. Now, before I tell you about tonight's event, I want to mention, as I did last time, that we have now started to ask for contributions to support this event. In order to keep Brain and Mind going for the next 10 years, or so we hope, we need a little of financial support. And although the college does continue to support us, we do need a little more than that, especially if we're going to bring in speakers from outside Oxford. And I hope you'll agree that sometimes it's really nice to get in some new blood and hear what people have to say who aren't in Oxford. And sometimes the real experts in the field are outside of Oxford. So it doesn't have to be a big contribution. A tenner here, £20 would be fantastically well received. And it would also help with the coffee and tea, which you get with nice cakes at the interval. Now, because of financial pressures, we've tried this year to choose our topics for discussion that would allow us, especially, to draw on the best local talent. And with this in mind, we came up with 3 topics associated with education and learning. Last term, we discussed Reading and the Brain, and it was a fascinating evening. Next term, we'll be discussing Science and the Brain. And the topic this term has allowed us to have as one of our speakers one of the members of the Brain and Mind Executive Committee, Dr. Ann Dowker. I'll introduce her properly when it comes to her talk. Okay, so maths is a subject that forms part of the fundamental building blocks of all our education, and it lies at the heart of the sciences. No doubt, few of us think about maths few of us think about maths any more than beyond what we're taught in those early school years. Some may be surprised to learn that the first mathematical texts were found in Mesopotamia and Egypt and can be dated back to 2000 BC. And the etymology of the word, I understand, comes from ancient Greece, mathema, meaning learning, something learned or knowledge. And it is from the ancient Greeks that we can trace much of mathematics. But much can also be traced to a subsequent period at the golden age of Islam in the 8th to 10th centuries. Today we can identify many branches of maths. To name a few: arithmetic, geometry, algebra, calculus, number theory, and set theory. As well as the subject matter of maths, there's our engagement with it. How does the child engage with the world of numbers? And how does our brain cope with numeracy? To tell us about these things, we have our three speakers tonight. And we'll start, as usual, with neuroscience, followed by psychology. So we'll have two speakers back to back. Then we'll have about a 15-minute Q&A, and I'll take questions from Hamburg and here. Then we'll break for tea. Then we'll come back and we'll have the philosopher, and then we have about a half an hour for a big Q&A. So we'll begin our evening, and I'll introduce the first of our speakers, Professor Roi Cohen Kadosh, who is a cognitive neuroscientist and psychologist specializing in brain plasticity, neurostimulation, and is interested in enhancing learning and cognition. He's head of the School of Psychology at the University of Surrey, and tonight he will talk to us about revolutionizing education. Roi.
Thank you very much for the invitation and the introduction. It really looks like a great event. I will start by telling you some of the neuroscientific findings and how do we use these mechanisms using neurostimulation to improve mathematical abilities, and then what might be the reason for that and how do we think we might going to use it in the future. So I would not start with the maths, although there is an equation there, excitation divided by inhibition. Excitation-inhibition balance is a way that we can quantify the interplay between neurons that are involved in excitation in the brain versus inhibition in the brain. It's in a very simplistic way what I provide here, but it has been implicated in different types of neurological and psychiatric conditions, and I provide here with a list. Now, it's not only implicated in those conditions. We could also see that excitation inhibition is also an important marker for learning and cognition. There are different ways how we can quantify excitation inhibition in the brain, non-invasively. One of the methods is using MR scanner, so MRI, and it allows us to look into different neurochemicals in the brain that are involved in excitation and inhibition and quantify that for each individual. Another way, also non-invasive, is using EEG. And also there are some methods that allows us to quantify excitation inhibition. So for example, when we're using magnetic resonance spectroscopy in order to quantify excitation inhibition in the brain, we could see that in healthy individuals, the level of excitation inhibition in key brain regions are linked to memory and learning. This is, for example, one type of study that shows how the level of excitation inhibition is changing as a function of learning. Okay, the more people they learn, the better they are. There are changes in areas that are involved in this learning, and you could see increase or decrease in excitation inhibition. When we thinking about maths, this is with a postdoc in my lab, now is a lecturer at the University of Swansea. George, what that we looked into there is the changes in excitation inhibition in the brain in those who continue to study maths for their A-levels compared to those who decide to not continue to study maths. Okay? What's happening in regions that are involved in learning, such as in the anterior part of our brain, and more specifically in area that it is called the middle frontal gyrus, that we could see it's linked to learning abilities. And what you could see is that by the concentration of GABA, which is an inhibitory neurotransmitter in the brain, you could predict whether someone is continue to study maths versus they stop to study maths. Not only that, by this level of these neurochemicals, that it is again an inhibitory neurochemicals, you could predict their success in a maths standardized test 1.5 years later. This is with magnetic resonance spectroscopy. I mentioned there is another method which is using EEG. This is with Ninka van Buren, who also was in my lab. And over there, in children, you could see that the level of excitation inhibition is linked with their abilities to perform simple arithmetic problems such as addition, subtraction, multiplications, and division. So it seems that there is a link between excitation inhibition and mathematical development. But a more interesting question is whether there is a causal role of excitation inhibition in mathematical development. What I showed you so far is only association. And in this case, brain stimulation could be a very powerful tool for us to change how the brain works, and then to show whether there is really a causal link between excitation inhibition and learning. In this case, mathematical learning. For that, we used quite extensively a method that it is called transcranial random noise stimulation. It's a method I will not go into details. If someone wants on the break, I'm happy to provide them with the specific details about that. It is, I think what is important to highlight here is that it's a low intensity neurostimulation method. It's painless. It is safe if you know how to use it, of course, like everything else. And it's non-invasive. It can influence the level of excitability in the brain, so it's increased the excitation of a region that you apply it over without eliciting action potential. And there are different ways to explain why it works. One of the dominant theories is based on something that is called stochastic resonance, and it's applied to a variety of phenomena that links noise to performance. In this case, at the neuronal level, what I want to show here is that if you have a neuron that it is fluctuating in the brain, so it needs to transmit information. But it needs, in order to transmit information, it needs to pass a certain threshold. If it's sub-threshold, it's not able to transmit this information. But what happens if you add to that noise, which is, you could see these spikes, gray, that is added to this fluctuating signal, you could see that it increased then the likelihood of this sub-threshold signal to pass the threshold and transmit the information. So this is an example how noise could be beneficial. Now, of course, I could not bring here neurostimulation and start to give it to you for you to experience that. But at the perceptual level, it's been known for many years that if you add noise, you can actually improve the performance of a system. And I'm going to show you that at the perceptual level. So throughout this slide, there is actually here a subthreshold signal. So there's a picture here that you're not able to reliably detect. I do not know if Adrian can see it from here. You could not reliably detect what it is there. And perceptually, if we add to that noise at the perceptual level, you could then see how it's improving the detectability of the picture. You could also see that if you add too much noise, it starts to degrade the level of perception. Okay, so the noise needs to be at a certain level. There is an optimal level to provide the noise to improve the performance of the system, in this case, your perception. Okay, same thing that we can do at the normal level to the brain. So we did something like that more than 10 years ago. This is with Albert Snowball, who did his undergrad project in my lab. This was the first study of its type back then. We gave to participants to learn arithmetic facts. So for example, 4 # 12 = 17. Doesn't make any sense. These are university students, actually in Oxford, quite good with maths. They had to learn these facts. When you give them the TRNS, the brain simulation, in red, you could see it compared to sham, which is placebo, okay? There is an improvement in their performance. This is based on reaction times, measured in milliseconds, okay? You could see that with days, there are 5 days here, they became better. There is increase in difficulty every day just to make it more challenging, but you could see overall there is better performance when they receive TRNS. What happened when we learn a bit differently? So not using drill, but based on calculation. So we asked them to apply an algorithm on a pair of numbers, just like, for example, the numbers here, and they need to come up with the answer. So it's much more demanding. And when they do that, you could see that, again, random noise stimulation improved their learning. They learn faster, better, and what you could see is that the performance here, it's on the milliseconds. It's, of course, much more difficult, this task. You could see that it's above 1 second, while here, if you learn by drill, you just retrieve it by heart. Okay, it's much easier, the task. I'm not going to show here. We examined their performance 6 months later. We invited the participants to the lab. The one who received stimulation for the algorithm only performed still better than those in the sham group, showing a long-lasting effect in this case. Now, what we recently showed, and this is again with Ninke, we examine how the level of each individual, the level of their excitation inhibition, is influenced by the stimulation they received. And I showed you the example based on the stochastic resonance. And what we found here is that if people had, before they received the stimulation, a low level of excitation inhibition, they benefited from the stimulation. Okay? If they had high level of excitation inhibition, they did not benefit from that. Only those who had low level of excitation inhibition. This is in line with what I showed you with the picture of the Big Bang. Okay? If the noise needs to be at a certain level. If you have an optimal level, and it's known from other fields that use noise to improve performance, if your level of performance is already very good, adding noise is going to detriment it. Okay, it's going to impair that. But if it's not as well, just like you could see in this picture here, in the example, if you add noise, it's going to be beneficial. This is just another finding from this study showing that indeed random noise stimulation led to changes in excitation inhibition. The graph, it's a bit reversed, but it's showing that the stimulation itself indeed increased the level of excitation inhibition in the individuals who received that. Now, one of the other findings that we applied based also on the theory of stochastic resonance is that in this case, if this is really the case, then random noise stimulation going to improve the learning of those who struggle with learning. Not those who are already perform very well, because the brain works quite at the optimal level, but those who really lag behind. For example, those with mathematical learning difficulties. So in this case, if we're going to apply the neurostimulation to the area that are involved in the mathematical learning difficulties, we would improve the function of this brain region and allow the individuals to perform better, to learn better. So we run a proof of concept study at Fairley House. This is a school in London for specific learning difficulties. This was with Chang Yen Lui, who completed her PhD with me. We gave to children to have training on a numerical game, so they had to learn things much more simpler than what we give to students. This is to learn, for example, the relationship between numbers, to have a more understanding of cardinality, link numbers to space, and this was over 1 month, 2 sessions per week. What we found there, very similar to other studies that use random noise stimulation to improve learning, is that those who receive the stimulation, they show a steeper learning, okay? They are able to learn better than those who receive sham. Now, a question that I've been asked quite frequently is, why is that? Why is it at the psychological level? Why do you find this effect? Is it only for maths? Is it for other areas as well? I can tell you that we have some findings showing that it's also improved vocabulary learning, for example, when you give it to people to learn foreign vocabulary. They are able to learn faster, they remember it better, and it's also lasting beyond just the stimulation session, indicating that we are changing how the brain works. One of the things that could be involved there is actually attention. The similar areas that are involved in learning, in cognitive learning, are the same area that are involved in attention. When people are able to be, where are people more attentive to the learned material, they're able to learn it better, they are more focused, and they will remember it for a longer period of time. There is some evidence for that. One of it is with colleagues that read my book that I published on the stimulated brain and contacted me in order to help them to develop a method to improve attention in those with ADHD. And when we applied the same protocol that we did in children with mathematical learning difficulties, but here to children with ADHD, you find very interesting findings. First of all, you see that in the case of TRNS, there is an effect on the level of excitation inhibition. The graph here is a bit flipped, so lower values here indicated increase in excitation inhibition. Okay, so there is an increase in excitation inhibition. I know the graph is a bit misleading, and this is in the case of TRNS compared to sham. You could see the level before they received the intervention and after 10 days that they received the intervention, and it's lasting for 3 weeks after. And it's also associated with an improvement in terms of their symptoms, in the children's symptoms, in the ADHD symptoms. So this is at the baseline and what happened 10 days later compared to sham. One of the challenges for the future is to see how we can find who's going to benefit from the stimulation, because I showed you that not everyone benefiting from that. It depends on the level of your the level of excitation inhibition. So how we can actually make a more personalized approach that could benefit more people from using this neurostimulation method. One of the ways to do that is to integrate with personalized, to integrate with neurostimulation AI, so artificial intelligence, in order to personalize the intervention. So this is something we developed a few years ago, and over there we're using an active machine learning that learned based on the individual characteristics and provide a recommendation what would be the neurostimulation protocol that's going to be most beneficial for them. The first time that we did it was actually on solving arithmetic problems. I'm not going to present it here. I'm going to present something that it is not on arithmetic, but very exciting. This is on attention again. What we did here, this is together with a company that we spin out based on these findings. What happened is that participant received to their home a neurostimulation headgear together with a tablet that is connected to a cloud. And based on their characteristics, they received a neurostimulation protocol that fits to their characteristics. So we are personalized it for each individual. While they receive the neurostimulation, they perform an attentional task. Okay, so this is called an air traffic controller task. They need to find out, I know it's quite sad to mention it after what happened last week, but they need to see when the airplanes are going, one of them going to be directed in the opposite direction to the others, okay? And they need to detect that. It's a very demanding, very boring task, but what we aim to do is to improve their performance while they're doing the task, with the idea that if we were able to do that, improving attention could, of course, be applied to other settings, including learning. So this was, just to say, this was a very ambitious project. I really need to give the credit here to Delia, who's doing her PhD with me at Surrey, Malin, who's actually completing her PhD here at Oxford, and Vune Goyen, who's developing the algorithms. So this is how the results look like based on the algorithm development. This is based on their baseline scores, so higher values indicate they are really good in the task, and this is the level of intensity that they received. Something very nice to see here is that the lower your baseline value, the greater the effect will have for the neurostimulation. So darker colors indicates an improvement in your performance. The darker it is, the more you improve. So it seems that those who benefited from that are really those who have a lower baseline compared to those who have already good performance. The other finding that it is, I think, important is from the next experiment, which we then applied the algorithm on new participant and saw what's happening. In this case, those who have low baseline performance, so those who really perform poorly, benefited the most from the personalized approach. It's called PBO. They perform, you could see the largest improvement in terms of their performance compared to non-personalized approach in red or sham stimulation. So this was found only in those with low baseline. You could not find this effect in those with high baseline. So it seems that the method is more beneficial for those with lower baseline. It has, I'm happy to discuss it later on, it has, of course, ethical implications when we think about enhancing people's ability and who the technology is going to be applied for. There are some concerns, of course, if you're going to enhance people's abilities, it's going to increase the gap between different individuals, so it's actually going to close the gap between individuals in terms of their learning potential. So this is a way that perhaps could help us to reduce the gap. To conclude, I showed you at the beginning how excitation inhibition balance can predict behavior, in this case can predict the arithmetic performance of children in this picture, how excitatory neurostimulation can change the level of excitation inhibition. And when we apply that, it could improve the learning of typical and atypical populations, whether these are university students or children with mathematical learning difficulties or ADHD. And it seems that we can already apply neurostimulation at home. Of course, potential other places could be a classroom. And with the help also of artificial intelligence, we can tailor neurostimulation parameters that going to maximize the effect of neurostimulation, and by that, opening opportunities for novel and effective interventions. I would like to thank you for your attention, and I would also like to thank my team and collaborators. Thank you very much.
Thank you very much, Roi. As usual, and we now move up a level, and we'll hear from our psychologist, who is Dr. Ann Dowker, who is a university research lecturer at the Department of Experimental Psychology here in Oxford, and a lecturer in psychology at St. Hilda's College and at Keble College. She carries out research on many aspects of developmental psychology and individual differences, and is especially interested in how these relate to education. She has a particular interest in children's mathematical development, and tonight she will talk to us about children's mathematical anxiety. Anne.
While we deal with this, I should point out that mathematics is a subject where attitudes to maths vary quite considerably, and anxiety and negative attitudes seem to be commoner than in many other subjects. So mathematics depends not only on our learning and intellectual abilities, general or specific, or on the teaching that we've had, but also on emotions and attitudes. So it's not just a purely cognitive subject insofar as one can ever totally separate cognition and emotion, but is one where emotions play a large role. And this is a picture that I rather like of what happens when things are going well, where this little girl is obviously very enthusiastic about the maths that she's doing. However, this is not universal, and anxiety and other negative emotions about maths are quite common. There are whole self-help books dedicated to dealing with anxiety and fear of maths. One quite popular book called Do You Panic About Maths? We don't have books that I know of entitled Do You Panic About Spelling? Or Do You Panic About History? Etc. So it does seem that maths is a subject that elicits some particular negative emotions. And this makes a difference also because research suggests a significant relationship between attitudes and performance. This has been found by a number of researchers in a number of countries, and in particular, maths anxiety and other negative emotions are often associated with worse mathematics performance. And as we'll bring up a little bit later on, this could be both because negative attitudes lead to poorer performance, and because poorer performance and failures make attitudes worse, but the former seems to play at least some part, and this makes it particularly important to study the development of attitudes to maths. And in general, with quite a lot of exceptions, young children tend to view maths quite positively. Most studies suggest that primary school children's attitudes to maths tend to be positive, they enjoy it, but their attitudes deteriorate with age during childhood and adolescence, as children and adolescents increasingly come to at best find maths boring and irrelevant, and at worst frightening. However, this doesn't mean that young children are always positive, and several recent studies indicate that even young children can show maths anxiety and other negative emotions. So for example, Petronzi et al. Reported significant maths anxiety in children as young as 5. And there can, and while most most studies show that attitudes get worse with age, Sorvo et al. Found that Finnish children in year 2 showed greater anxiety than children in later elementary grades, whether this is due to something to do with starting school relatively late in Finland or something to do with Finnish schools practicing some positive practices which improve attitudes to maths during primary school, we don't really know. And some studies also suggest that relationships between attitudes and performance can change with age, and that, for example, maths anxiety may have a more negative association with performance in older children than in younger children. Dowker et al. 2012 obtained some results which indicated that in primary school children, performance is related to self-rating in maths, but not to maths anxiety. On the other hand, some other studies by Wu et al. And Vukovic et al., for example, found that maths anxiety correlated with performance even in the early years of elementary school. Gender is also something that comes up. Most studies suggest that females have less positive attitudes to maths and are more anxious about it than males. Not every study shows this, and some people suggest that it might be more that females are more ready to admit to anxiety about maths, but it does, on the whole, seem as though females worry more about maths, and that this may contribute to females being more likely to give up maths after compulsory age and not to continue in careers that may involve maths. So in the rest of this talk, I'll be talking about a study that we did involving comparison between age groups in elementary, primary, and secondary school. Most studies haven't compared age groups from early primary to late secondary school in one study. And the study that I'll discuss here was carried out with 2 of my students, Olivia Cheriton and Rachel Horton, and it compares early primary, that's year 2, early secondary, year 9, early primary, year 2, late primary, year 6, early secondary, year 9, and late secondary, year 12. And the aims were, first of all, to investigate age differences between pupils in these respective year groups with regard to their attitudes to mathematics and also their actual performance, and secondly, to look for any gender differences in attitudes and performance. So, what we expected was that attitudes would be more negative in higher than lower year groups, as this is often found. We expected that corresponding to some previous studies, self-rating would be the strongest predictor of performance in primary year groups, but that anxiety would be the strongest predictor of performance in secondary year groups. And as regards gender, we expected that there wouldn't be a difference between girls and boys as regards their actual performance, but that girls would have more negative attitudes and especially greater anxiety than boys. So, in this study, there were 216 pupils in all who took part in the study, approximately equally divided as to gender, 59 pupils in year 2, 53 in year 6, 50 in year 9, and 54 in year 12. So that, for anyone who isn't in the English system, year 2 pupils were age 6 to 7, year 6, 10 to 11, year 9, 13 to 14, and year 12, 16 to 17. And the year 2 and year 6 pupils came from the same large state primary school. The year 9 pupils came from a non-selective state secondary school. The year 12 pupils came from a sixth form college, and all educational institutions were located in or near Richmond-on-Thames. So they were given the mathematics attitude and anxiety questionnaire, which was one that Gemma Thomas, another of my students, and I had developed to be usable with primary school children. We developed it in around the year 2000. And in this questionnaire, children rate 7 school mathematical activities, such as written sums, mental maths, understanding the teacher, etc., from 1 to 5 on 4 5-point pictorial scales, which I'll show you in a moment, which are how much they like the activity, how good they think they are at the activity, how unhappy they would be if they find they can't do the activity, and how anxious they'd feel if they can't do it. And possible scores on each scale ranged from 7, if they gave 1 the lowest, to every scale to 35, if they rated everything 5 the highest. And I will talk here just about liking, self-rating, and anxiety. Unhappiness at poor performance had somewhat similar results to anxiety, not identical with it, and if people want to know more about it, they can ask me. At present, I'll show you the rating scale, where for how good you are, a scale ranging from a large tick, if you're very good, to a large cross, if you think you're very bad at it. A scale from 2 wasps, really don't like maths, to 2 sweets, if you really like it, and a standard smiley faces scale from big smile to big frown, for how much, how happy or unhappy you would be if you couldn't do something, and a scale based on Roger Hargraves's Mr. Men, for going from Mr. Worry to Mr. Happy, for how worried or relaxed you would feel. And we looked at the effects of age and gender, where we compared the year groups, and we compared boys and girls. So age, year group, and gender were the grouping factors, and the actual scale score in the basic number of skills test, and all the attitude measures were the dependent variables. All were scored in a positive direction, so the anxiety scale was scored so that the higher you scored, the less anxious you were. So it's basically non-anxiety. So an average basic number skills score at any given age was 100, and there was, which, given that the scale is adapted for age, there shouldn't really be. There was a significant effect of year group on basic number skills, so that year 2 and year 9 did better than year 6 and year 12. This may have something to do with the nature of the subjects pupils were taking in year 12. Also, it was sixth form college rather than the primary or secondary school. But Gender, however, did not have any association with arithmetic test performance. At all ages, boys and girls were performing equally. So as regards self-rating, the mean self-rating scores out of a possible score of 35 went down from 28.85 at year 2 to 24.11 at year 12, and there was a very significant effect of year group on self-rating. The older you are, the lower you rated yourself, and this effect remains significant after controlling for actual test performance. So it can't be explained by the fact that perhaps the year 12 kids were on average doing less well. And so here is a graph of it, which I think shows how the self-rating scores are going down with age. There was also an effect of year group on liking for maths. Once again, liking for maths went down with age, and the effect again remained significant after controlling for maths test scores. And again, of course, it's in the direction of people liking maths less as they get older, as you can see from this diagram, with particularly marked decrease at in year 12. And there was, unlike for the previous attitudes, a significant main effect of gender, so that boys liked maths more than girls. Boys also rated themselves higher than the girls, but they didn't actually do better than the girls. So as regards anxiety, or rather non-anxiety, again, rather dramatic decline with age, so that with, in particular, primary school pupils being markedly less anxious than secondary school pupils. And interestingly, there were no significant gender differences this time. The girls rated themselves lower than boys and liked maths less than boys, but they weren't actually more anxious than boys. So, did the attitudes actually predict maths score? We did multiple regressions to see whether they did, with the basic number skills standard score, the actual maths test score, as the dependent variable, and the attitude scores as predictors, and self-rating was a significant predictor, but no other predictor was significant. So there wasn't obvious prediction of liking for maths or maths anxiety on actual score. Please, I mean, I don't know, I'm getting computer anxiety. It's, all right, this work now. Okay, so results were similar for each year group separately and for each gender separately. Self-rating was the only significant independent predictor of performance. The exception was the youngest kids. In year 2, no attitude variable was a significant predictor of performance for these youngest children. And so we had predicted that self-rating would be the main predictor of performance in the younger children and anxiety in the older children, but there was actually no difference. It was self-rating both in primary and secondary. So, what conclusions can we draw about age differences? The study does support the hypothesis that attitudes to maths decline with age, as regards all attitude variables. Contrary to predictions, self-rating rather than anxiety was the main independent predictor of performance among older as well as younger pupils. It would be desirable to carry out longitudinal studies of the same pupils starting early in primary school and following them up to and through secondary school with them all being different groups. It can be difficult to say whether this was the effect of age universally or whether it might be due to changes in the education system over time, for example, of which there have been quite a lot. But data was collected, by the way, shortly before the pandemic, so that wouldn't have affected the results. But longitudinal studies of the same pupils would be very interesting, but obviously would be rather practically difficult to do over such a long period. As regards gender differences, girls and boys performed equally well in maths. Girls liked maths less than boys and rated themselves lower, but they didn't show greater maths anxiety. There are a few questions arising, apart from the $64,000 question about why so many people are anxious about maths and why it seems to be stronger than for other subjects. So that one would, of course, need to do more systematic comparisons with other subjects. An important question is what's the direction of the relationship between maths performance and self-rating? Are success and failure in mathematics being reflected in self-rating so that people rate themselves according to how they've actually been doing in tests? Or is it more that self-rating affects performance? Very likely it's both. Most studies show bidirectional relationships between attitudes and performance. And should we have more interventions for maths performance, for attitudes, or for both at the same time? And when should such interventions take place, if they do at primary school or later, perhaps when the attitudes are becoming more negative, or indeed are there things about the curriculum in general or approaches to teaching that should be changed to ensure better performance in maths in this country, which many studies suggest is not at the highest possible level, and to ensure more positive attitudes. So thank you very much for listening. I do apologize for the computer's rather odd behavior at certain stages of the thanks a lot.
Thank you, Anne. Okay, well, let's take about 12 minutes for questions. And the questions can be to either speakers. And Hamburg, I'll ask you in a moment. I'll start with one here in Oxford.
This is a question.
Is it on?
Is it on? Is it on? Yeah.
I don't know. Is it on?
Yes, it is. The question for Anne. I'm probably missing something. But can you explain? You said that self-rating is a predictor of performance. That girls tend to have a lower self-rating than boys, but girls and boys perform equally well.
That's right, which has actually been found in some other studies. So overall, self-rating predicts performance in maths, but it doesn't seem to be why. It doesn't seem to have an effect on gender differences, unless perhaps we may speculate that perhaps girls would be doing better at maths if they weren't rating themselves lower.
So those three propositions are compatible, are they?
Yes.
I can't see how they are, but
I'm
sure they are. People can, in general, overall, self-rating seems to be associated with performance, but it's not the case that the
that girls and boys differ in performance, despite the fact that they differ in self-rating. Now, it could be that, for any number of reasons, it could be that girls, as I said, might be doing better at maths if they rated themselves higher. It could be that maths anxiety is more important in predicting, in gender differences, in predicting maths performance, and that the gender differences, and that here there were no gender differences in maths anxiety.
Okay, let me just ask in Hamburg. Do you have a question, Micah, from Hamburg?
Yep. Hi, we have a question, or I have a question, namely on the performance of math and liking math. What effect do the early university years have? Because this is personal experience, but I wasn't very passionate about maths in school times, but then having a specific subject in university that I was passionate about gave me access to math, and that could also be related to why maybe children don't like math.
Sorry, I didn't hear the last part of the question.
Could you just
repeat? Yep, sorry. So I was saying that maybe the passion for something specifically, like a use case of mathematics or a more applied version of it, can ignite, well, passion and then also improve performance in math. And what does the data say? Is there maybe a dip up after school finishes and people go to university and maybe they realize, oh wait, I need math for biology, or I need math for XYZ, even psychology, etc.?
Well, I think the thing is that while it may be that some secondary pupils who have a long-term plan do work on their maths to achieve it, there are also an awful lot of people, especially perhaps here girls, who restrict what subjects they choose to do at university because they wish to avoid maths. So that it isn't always the case that wishing to do a subject at university makes you persist with your maths. It may be that not liking maths makes you not choose certain subjects at university.
Thank you. I think we have a question from the middle here. We'll start here and then we'll, yeah. Barnaby, can you? Yeah, Lynn.
Thank you. A question for the first speaker, please. You spoke about noise and the difference that random noise made. I wonder, for a layperson in neuroscience, you could clarify what you mean by noise, and does it have any connection with music and the well-known effects of Mozart and Bach, for example?
Thank you for the question. So when I'm talking about noise, in what we do is actually electrical noise. So you're sending a current that is fluctuating quite fast in different frequencies with a distribution that it is set eventually on zero. So it's white noise. That's what I mean by that. If links to music, not in this case, but there have been some other studies that talked about noise at the perceptual level. So, but that's a different topic than what I'm doing.
We have lots of questions here. Can I quickly ask, is there another question in Hamburg?
Yeah, thank you very much for these great talks. Question for Anne. What do you think, like how geographically specific are these results of your study?
Could you repeat that?
Just say that again, how what specific?
Geographically specific, like it was conducted. Yeah.
Yes. Well, given that in this particular study, everyone was in pretty much the same area of the country, I wouldn't think that it made a difference to the results here. There are a number of studies which look at broader geographical or national differences, and there are a lot of international differences in actual performance in maths, and in almost every country where it's been studied, there's a negative relationship between anxiety and other negative attitudes and performance. there is the differences between countries in maths anxiety are only partially related to differences in actual performance, so that on the whole, pupils in relatively high achieving European countries, such as Finland and Estonia, also tend to report, and the Netherlands also tends to report relatively low maths anxiety. On the other hand, in the East Asian countries, where pupils tend to do particularly well in maths, they tend to report high anxiety, though within each country, anxiety is negatively related to performance. Of course, it can be difficult to tell how much is due to cultural differences in willingness to admit to anxiety, but there does seem to be, on the one hand, a fairly consistent relationship between anxiety and performance. On the other hand, you can't easily explain international differences in anxiety by international differences in performance, or vice versa.
Thank you. Okay, we have some questions. Do we have one back there that I missed, Chiara? Okay, that. Yeah.
I know. Oh yeah, there we go. I had a question for the first speaker. Thank you all for your talks. But I was wondering, how big is the effect size of the interventions you're doing? I don't know if you've studied it already, but let's say in a grade, would you go from like a 5 to a 10, or is it more like 5 to a 6, so small difference? How big is the effect size?
It's a great question. When we quantify the effect size on multiple studies, it seems to vary between effect size of 0.8 to 0.1, so it's considered to be a large effect size.
I'll take one more here and then one more from Hamburg.
Okay, thank you. I have a question for Professor Cohen Kadosh as well. I'm wondering, what's the relation between like electric noise, as you're using there, and the notion of noise in something like the predictive mind, or like the free energy principle, or something like that, in a like more abstract model of the mind?
Yeah, it's a great question. I do not have any experiments that examine that, or that I can tell you what is. I can only speculate here. So for example, there are some computational models, things like that, that insert noise into the system and so on. It seems that the system can perform better when you insert the noise. It's not surprising. I know that it's counterintuitive to us, because noise is something that probably have a negative connotation. But I was very surprised when I read, on varied topics, going from, for example, semiconductors to geography, how noise implemented in different fields, and you could see that they can actually predict performance and improve performance.
Okay, I'll ask again in Hamburg. Do we have another question there?
Yes, we have 2 more questions.
We'll take one, Mike, and then save the other one for the longer question period later.
Okay.
Go ahead.
Yes, also related to the first speaker. Do you make a connection between the area of neuromorphic computing and reservoir computing, which is I'm not sure if you can hear me well.
Yes, we can.
So in the domain of analog computers, there's this paradigm being explored called neuromorphic computing, where there are many implementations. One of them, they throw like nanofibers sort of in a random arrangement, and then use linear regression to make some sense of the processing that takes place in that reservoir. And they use this term called criticality or edge of criticality to optimize, something about the reservoir. It's quite abstract, but I'm wondering if you make a relation there or a connection to your research, and how this state of randomness and edge of criticality affects brain performance.
Thank you very much for the question. It's a brilliant question. I will admit that it is really beyond my field of expertise. What I can just say that is in neuroscience, criticality is also been assessed. I assume it's derived from very similar ways, and it's also integrate noise in that. So it's also a way to assess how there is a cascade of information and decay that has been linked to excitation inhibition and therefore also to the noise in the system.
Okay, well, great questions. If you have more questions, hang on to them because we have a longer Q&A at the end after the philosophy talk. But now we're going to break, and there's tea and coffee and cake outside. So I encourage you to go out, get your tea quickly because we're in 15, 20 minutes. I'm going to get you back in. So go out, get your tea, say hello to the person next to you, and I'll see you back here in 20 minutes. All right. That was amazing. We seem to have more time for tea than usual. So if we settle down, we'll now continue the evening with our final speaker, who is Professor Adrian Moore, who is Professor of Philosophy at the University of Oxford and Fellow of Philosophy at St. Hugh's College here in Oxford. His many publications include Gödel's Theorem, a very short introduction. Some of you may know it. And some of you who listen to Radio 4 may recognize his voice, as in 2016 he presented a 10-part BBC series, History of the Infinite. Tonight he'll be talking to us about mathematical powers, those of human beings and those of computers. And no PowerPoint, so we don't have to worry about that.
Very low tech. Thank you, Anita, for the introduction. You mentioned one of my publications, the book on Gödel's Theorem, and it's actually Gödel's Theorem that's going to be the focus of my remarks this evening. And I want to talk about the bearing of this theorem on the question that is my title, whether the human mind has mathematical powers beyond those of any possible computer. Gödel's theorem is a famous result that was established almost a century ago, actually, in 1930, and many people have thought that it does have a bearing on this question, and my aim this evening is to try to give you some indication of the bearing that it is thought to have. But before we go any further, I want to talk a little bit about geometry. Right at the very beginning, when Anita was introducing these talks, she pointed out that mathematics is divided into various different branches, and Gödel's theorem is specifically concerned with arithmetic. And I'll say a little bit in due course about exactly what I mean by arithmetic. But it's helpful, actually, before we get on to arithmetic, to think specifically about geometry, because geometry provides us with a kind of paradigm that is relevant to what Gödel's theorem tells us about arithmetic. And I don't know whether people still learn mathematics at school in the same way that I did, but when I was doing mathematics at school several thousand years ago, one of the branches of mathematics that we studied was geometry, and we studied it in what is known as an axiomatic way. And what that meant was that we were supplied with some very, very basic principles that we were just allowed to take for granted, things that were self-evident or obvious that would be classified as axioms. So an example is that between any 2 points, you can always draw a line, or that any given line can always be extended indefinitely far. And then on the strength of those very basic principles, on the strength of those assumptions, we were tasked with proving more and more complicated results, and with seeing how they could be used to establish more and more complicated results. One of the most famous examples of all being Pythagoras' theorem, that the square on the hypotenuse of a right-angled triangle is equal to the sum of the squares on the other two sides. And this paradigm, this axiomatic paradigm, it goes all the way back to the ancient Greeks. Euclid is the name that's associated with this paradigm because Euclid was the person who presented these very fundamental principles on the strength of which these more and more complicated results were established. Now, by modern standards, Euclid's efforts can be criticized, actually. I mean, they were remarkable. It was incredible that Euclid was able to do as much as he was able to do. Contemporary mathematicians would take issue with some of what he did, and they would want to introduce further basic principles that he took for granted without specifying them. But nevertheless, be the merits of his particular efforts as they may, the fact of the matter is that they present us with this paradigm of showing how some fundamental principles, a finite stock of fundamental principles that can be taken for granted, can then be used to establish more and more complicated results. And that was something that was established specifically in connection with geometry. Now, Gödel's theorem bears on a very natural question, which is, can we do the same for arithmetic as we can do for geometry? Is there some kind of analog? Could we specify a finite set of fundamental principles that we can take for granted, on the strength of which we can establish all that we want to establish in arithmetic, including very basic things like 7 plus 5 equals 12, but also including much more interesting and much more complicated results, such as that there are infinitely many primes, for example, or that every positive integer is the sum of 4 squares. Now, I said that I would specify exactly what I meant by arithmetic, so just to be clear about this, for these purposes, by arithmetic, I just understand the study of the positive integers, 1, 2, 3, 4, etc., and the various operations that apply to them, like addition and multiplication. So that's all that we mean by arithmetic in this context. So we're not even interested in fractions. As far as the study of the positive integers is concerned, we don't even recognize that there's any such thing as 1 divided by 2, for example. So there's a sense in which it's pretty basic what we're considering. And so you might well think that what we can do in the case of geometry, we surely should be able to do in the case of arithmetic as well. Surely we can specify some basic assumptions about the positive integers that can then serve as axioms for proving more complicated results. So, for example, one of the things that you might think we can absolutely take for granted is that if you multiply any number by 1, you get the same number. And then that presumably is going to be relevant to some more complicated calculations, such as 671 times 49, let's say. At a certain point in that calculation, you will want to multiply a number by 1, and it'll be important what happens when you multiply a number by 1. But although it's a very natural question whether we can do the same for arithmetic as we can do for geometry, nevertheless, it was literally thousands of years after Euclid before attempts were made to do it. And people weren't sure whether they had succeeded or not. And basically, what Gödel's theorem tells us, what Gödel established nearly a century ago, was that we can't do for arithmetic what we can do for geometry. If somebody comes along and specifies a certain stock of basic assumptions that they say we're allowed to take for granted, and the question arises whether that's fixing all that we want it to fix for us, Gödel's theorem tells us that something will have gone wrong. Either we will overshoot or we will undershoot. We will overshoot if we find that we can establish all the things that we want to establish, but only at the price of establishing a lot of rubbish as well. Somewhere in amongst our basic assumptions, there'll be something that's incorrect and that is giving us some incorrect results as well. That would be an example of what I mean by overshooting. The opposite problem, the problem of undershooting, is specifying basic principles that are correct and don't lead us into error in that kind of way, but are insufficient to establish everything that we want them to establish. So we're trying to perform a kind of balancing act here, and Gödel's theorem is a way of showing that the balancing act can't be performed. We always fall one side or the other. Another way of putting this is to say that no finite stock of fundamental principles, fundamental arithmetical principles, will enable us to prove the whole truth and nothing but the truth about arithmetic. We can do each of those things, but we can't do them both at once. We can devise principles that enable us to establish the whole truth about arithmetic. We can do that, but only at the price of enabling us to establish rubbish as well. So there might be some basic principles which will eventually put us in a position to prove that 7 plus 5 is equal to 13, for example. And we don't want them to do that. We don't want to introduce errors into our arithmetic. So we can establish the whole truth, but only at the price of establishing more than that. Conversely, we can avoid that problem and establish nothing but the truth, but only at the price of falling short of where we want it to be and having some arithmetical truths that we can't prove. So any finite stock of basic principles that you come up with will either establish the whole truth about arithmetic or establish nothing but the truth about arithmetic, but never both. You're always going to fail in one or other of these two ways. You're always either going to overshoot or undershoot. Now, given the choice, we'd much rather undershoot than overshoot. One of these errors is much more egregious and much more serious than the other. Basically, it's a choice between errors and omissions, and we'd much rather that our system, our set of axioms, contained omissions than that it contained errors. So let's assume that we've at least got ourselves into a position, we've got some finite stock of basic principles. We're at least assured that there are no errors there. The issue is that there are omissions. There are things that these principles are not enabling us to establish. So to use the word that Gödel himself used in this context, they're incomplete. Nevertheless, the way in which Gödel established his theorem meant that if we're in that position, if we've got a finite stock of basic principles that we can see are error-free, the very fact that we can see that they're error-free gives us a clue about how they should be supplemented. We know that they should be supplemented. Gödel's theorem tells us that as they stand, they're incomplete. But just recognizing that what we've got is a decent set of axioms puts us in a position to see what we have to do to provide ourselves with an even better set of axioms. So we can advance from this incomplete system that we've got to one that's better, but still incomplete. Gödel's theorem will still apply. We're never going to be able to hit the whole truth and nothing but the truth. So we can improve on what we've got, but that process of improvement will carry on indefinitely. We never get exactly what we're after. Now, you're probably sitting there thinking, this is all very well, but what does this have to do with the human mind and computers? So let me, in the few minutes that remain, let me try and give you some indication of what the connection is. There are two Oxford people who are well known for having argued on the strength of Gödel's theorem that the human mind has certain capacities that no computer has. The philosopher John Lucas and the mathematician Roger Penrose. The argument is associated with these two people in particular, and it's often referred to as the Lucas-Penrose argument. And I want to present it as briefly as I can, and then to present some counter-arguments. I won't offer my own verdict on this. I'll just present you with the argument itself and then some things that people have said to counter it. And then, leave it to you or leave it to the discussion to think some more about how we might arbitrate. But the argument goes as follows. What Lucas and Penrose argued was that if a computer is going to do arithmetic for us, and after all, computers do that sort of thing, long before we reached the point of sophistication that we're at today, there were pocket calculators that would add and multiply for you. But surely, Lucas and Penrose say, what the computer is doing is operating with some basic principles that you've fed into it, that you've programmed it with. And so by Gödel's theorem, the computer will be limited. It'll be able to do a certain amount for you, but it won't be able to do everything for you. No computer could be programmed to discriminate between true arithmetical statements and false ones. So given any computer and given its program, that program will be deficient in a certain way, and in the way that I tried to explain earlier, we have the resources to see how it must be supplemented. So in the nature of the case, the computer itself is subject to a limitation that we're not subject to. And so the thought is, whatever a computer can do, given any computer which is operating with some basic principles, we are always in a position to see how those principles can be improved upon. And so the thought is, there are basic mathematical abilities that we human beings have that can't be matched by any possible computer. That's the argument. And then the counter-arguments, the reactions to this, have basically fallen into two classes. Roughly speaking, there are those objections which take the form they've underestimated what computers can do, and there are those objections that take the form they've overestimated what human beings can do. So, have they underestimated what computers can do? Well, that's obviously a really interesting question, and maybe we can pursue it in the Q&A. But you do wonder whether Lucas and Penrose would have been as inclined to advance their argument if they'd been familiar with ChatGPT. It's not clear that the only way in which a computer can do arithmetic for you is by being fed some fundamental principles or axioms on the strength of which it establishes results. Maybe a computer will work by being programmed in such a way that horrendously complicated subprocesses just result in a configuration on the screen as of the number 12 when you ask it what 7 plus 5 is. But it hasn't proved that from any basic principles of arithmetic. So that's that thought. And then, have they overestimated what human beings can do? Well, maybe they have. The way that I put it was, given any stock of basic principles of arithmetic, we can always see how they can be improved upon. But how clear is it that we can be given any stock of basic principles of arithmetic? What if there was a stock of basic principles that some computer was working with that was nevertheless finite, admittedly, but colossal and incredibly complicated and beyond our abilities to grasp? So maybe they've overestimated what human beings can do. Now, I'm conscious of the time, and there's plenty more that I could say, but Anita did say that I had to limit this to 20 minutes. So I shall finish very soon. But just to flag some of the things that we might discuss in the Q&A if people are interested, as far as this limb of the argument is concerned, whether they've overestimated what human beings can do. How important is it, for example, that we're only interested in what human beings can do in principle, not in practice? Does that have a bearing on the argument? And if so, what bearing does it have? So there's all sorts of issues, obviously, that we can explore in greater depth, depending on what people are interested in. Thank you.
I was going to mention at the start that some of you may know this and some of you may not, so it's worth mentioning. In Oxford, you can't do philosophy on its own, and one of the schools that we have students study for is maths and philosophy, and that's the school that Professor Moore is associated with. So you get the philosophy and the mathematics. Okay, so now I think this time, Micah, I will ask if Hamburg has a question to start with. It can be for any of the speakers. It doesn't have to be only on the last.
Thanks very much. Thank you for the fantastic talk, Adrian. If I may say so, this is Max, Adrian, I was wondering if you had any thoughts on the relation between human embodiment and the kind of potential that humans have, mathematical abilities that computers lack because they don't have a body. They don't have that kind of conscious experience. Is that something that you have considered or explored in any way?
Not in this connection. It is obviously a really interesting question to what extent sheer biology is relevant to the capacities that human beings have. And I suppose my gut reaction is to think that, fascinating though that question is, it's orthogonal to the issues that arise here. But it may be relevant to the thing that I flagged right at the very end, which is whether we ought to be interested only in what human beings can do in principle, not in practice. In practice, there are all sorts of limitations that we're subject to simply by virtue of the fact that we're embodied and finite creatures, which will inevitably set a bound on the complexity of what we can deal with, or the number of basic principles that we can deal with. I kept using the word finite. I kept saying that what we were interested in was a finite stock of basic principles that we were going to use as axioms. And in practice, when you think about axiomatic approaches to mathematics, finite tends to mean pretty small. So Euclid's axiomatization of geometry, for example, is famous for only having 5 fundamental geometrical assumptions that it made. But of course, you could have a system that had a set of basic principles that was only finite, but unbelievably large. You know, I mean, there may be more of them than there are nanoseconds between now and the heat death of the universe. And so any human being trying to grapple with those would immediately be snookered. Sheer bodily limitations mean that no human being could reckon with a system that had that many axioms. So our bodily limitations are obviously relevant there in practice. And then the question arises, are we nevertheless entitled to prescind from those practical limitations and just talk about what human beings can do in principle? And I mention this for the very simple reason that both Lucas and Penrose are inclined to make this move, actually. They both emphasize that they're only interested in what human beings can do in principle. So all sorts of difficult questions are swirling around at this point. I mean, what is it to consider what a human being can do in principle, and how much are we allowed to vary? Would it just be a matter of having a much, much, much bigger body and living for a much, much, much longer amount of time? Or are we interested in somehow having a very different kind of body, and might that be relevant? And so, of course, those are issues that this question raises.
Out of curiosity, is that Max in Hamburg?
Yes, I think so.
I thought I recognized the voice. Okay. Do we have a question here in Oxford?
For the third speaker, on the topic of of Gödel's theorem itself, if you establish that you can create this finite set of axioms where it's correct, but there's some rubbish in there that's incorrect, but it's sufficient to be axiomatic. Given that there are some correct axioms in there, would it be reasonable to say that you could take a subset of those axioms that is completely correct but incomplete, and would then that suggest that somewhere between the subset that's correct but incomplete and the whole set that's complete but incorrect, there is a single axiom that turns the tide, or from undershooting to overshooting?
That's a very, very natural suggestion. We've got these 2 ways of going wrong, undershooting and overshooting, and immediately the thought arises, okay, so why can't we just find something that's bang in the middle and gets us exactly what we want? So it's a very natural question that you're raising, a very natural suggestion that you're making. And I guess one of the reasons why Gödel's theorem is so striking is that exactly what it does is answer that question negatively. And it tells us, no, we can't hit the sweet spot. The very thing that we want to do is the very thing that Gödel's theorem tells us that we can't do. For sure, I mean, maybe I'm misunderstanding your question. For sure, it follows that if one theory gives us less than we want, and another axiomatic theory gives us more than we want, for sure it follows that there is such a thing as what we want and that it's between those two. That's certainly true. But what Gödel's theorem tells us that we can't do, we can't devise a finite stock of basic principles that'll give us what we want, that will enable us to prove just that, neither more nor less.
Okay, I'll go back to Hamburg. Do you have another question there, Micah?
Yes, we do. For the speaker, please. I was wondering, you showed that for high-performing people, there was no improvement with your stimulation paradigm. Does that mean that there's a to humans, or does it mean high performance?
So, Micah, you're cutting out a little bit. Can you just say it one more time?
I'm wondering if the high-performing people who saw no improvement with the stimulation, if that means that there's a limit to performance, or does it mean you need a different stimulation paradigm?
That's a very good question. So I had in the break some nice discussions with some of the people here. Just to say that we also try, not with the personalized one, but we try to use the stimulation methods with high achievers. So basically in maths, these are mathematicians. When we applied it to mathematicians, we actually saw an impairment in their performance. Okay, this is going very much in line that the system is really optimal. Noise is going to be detrimental. If you remember the picture of the Big Bang, you had too much noise. The picture is really good. You had noise. It's actually going to impair that. So it might be that this is the stimulation methods, and another stimulation method working on a different mechanisms could further enhance those that are already perform well. This is a hypothesis. We need to test it with different methods and see if there is something that can happen. But at least with what I've shown, it seems to be, at least with this method, there seems to be a limit. I'm quite happy with it, I have to say, because I worked also with neuroethicists here. And of course, the concern is what will happen if your stimulation going to increase the performance of those who are already, well, they're beneficial for that, but there also could be some risks.
Do you have a question? I think we have one here.
Thank you for the interesting talks. I have two questions to the first speaker. First, if you could say a little bit more about this excitation and inhibition, is that, and how the frequency of the brain waves, how much or how little they work in different areas? And then the second question on what would be then, if this were put into practice and, for example, used with children in classrooms, what would be a kind of dosage paradigm? So do they, I don't know, recharge once a week or a little bit every day, or is that kind of longer term, so monthly dosage, or I don't know how, so something along those lines.
Yeah. Thank you. Thank you for the question. So just to clarify, there are different ways to quantify excitation inhibition using different methods, and using different measures to quantify this excitation inhibition. So for example, with magnetic resonance spectroscopy, it's going to be based on neurochemicals, the ones that are involved in excitation, like glutamate, or in inhibition, like GABA. With measures like EEG, that they are usually based on the they're affected by the frequency, taking into account high frequency as excitation compared to lower frequency as inhibition. So very similar to what I think you implied. In terms of, this is one thing, and I'm actually writing now a paper showing how they actually do not measure the same thing. They actually could lead to different results, even opposite results than what people would expect theoretically. So with MRS, with spectroscopy, you find different results for one group of patients opposite than EEG, but it's a different topic. Just to show how much I'm excited about it. As for the dose, in terms of really going from the lab to more ecological settings, like you mentioned, classroom, just to say that my view is not going first to the children with atypical development. I see it more in terms of those who at the university, maybe things like widening participation, like if there are people that are in foundation year, for example, needs to improve their learning of some specific materials like math in order to that some career opportunities will open to them. How long will it need to be done? It's a very good question. This is one of the things that we want to examine because it also could affect how optimal the treatment is going to be. But from different studies that we run so far, it seems to be that there is no detrimental effect, at least if you use it for 10 consecutive sessions. Once you finish with that, it seems already to give them the boost to continue and benefit from that stimulation. So you don't need to top it up. In different studies, it's been examining the long-lasting effects. It seems to last for months. It might need to have some top-up in the future, but it seems to last beyond just the time of the stimulation itself.
Let me just ask in Hamburg, do we have another question?
Yep, we have another question regarding Gödel's theorem, or the incompleteness theorem. So is there a relation that can be drawn to the Heisenberg uncertainty principle or physics more generally?
Sorry to give you a very disappointing answer, but I'm pretty sure the answer is no. I mean, you're always at the mercy of somebody coming along and establishing connections that are unexpected. And it's the kind of situation where it is very tempting to draw connections, but sometimes those temptations are to be resisted. And as far as I can see, there isn't any interesting way of linking these results, I'm afraid. I wish I could give a different answer, but that's certainly how it strikes me at the moment. I mean, the jury's always out with these things. You're never able to say that one thing has absolutely nothing to do with something else. But I don't see anybody as having established any interesting connections between these.
Thank you. Do we have another question here? Oh, we have a few. Okay. Can we have the one in the back? Yeah? Yeah, right there. Oh, okay. Okay, it's fine.
Thank you for the talks. I have a couple questions for the first and third speakers. So for the first speaker, one of the things you mentioned was that ADHD symptoms are improved with the following treatment. Is there any evidence for ADHD subtype specificity? Because you mentioned that attention was one of the things that might be improved, and attention deficit is one of the main subtypes of ADHD alongside hyperactivity disorder. So is there any evidence for, again, subtype specificity of treatment efficacy?
Yeah, it's a very good question. So to give you a bit more details about these RCTs, so we combine the stimulation together with a cognitive training that target executive functions. So people with ADHD, children with ADHD most of them have an impaired executive function. When the sham receive the same thing. Yeah, they receive executive function training just with placebo stimulation. Yeah? So it aims to target not only attention but also impulsivity. yeah, because we target, for example, things like inhibition. When we target the brain, we target both the areas that are involved in attention and the impulsivity, hyperactivity type. And we find that the effects were not limited to one subtype, but actually when you look on the scale, you have the attention and the hyperactivity, impulsivity subscales, and it seems to affect both of them.
Thank you. And then for the for the third speaker, so one of the things you bring up is that potentially the differences between a human and a computer is what potentially allows us to have an understanding per se that isn't otherwise facilitated because we have an axiom upon which a computer is operating. Is that in any way different for a human though? Because I'm going to cite the anthropic principle that any life form that becomes developed enough will ask questions about why it exists. Is there anything particular about a human that makes it any different from any other biological computing machine that would put it in better stead than effectively another computing machine that we call a computer?
I think you're raising a really interesting question about as it were, the structure of the argument. What the Lucas Penrose argument is designed to do is to show that there's a certain sort of self-consciousness about the limitations of what we're working with that enables us to advance beyond those limitations. And in particular, if we're looking at the limitations that a computer is subject to, we can see how those limitations can be overcome. And then the question does naturally arise, well, even if that's true, is it inevitably going to be the case that there's then the possibility of some intelligence that stands in the same relation to us as we stand to the computer? And it is a very natural sort of progression, extending the original line of thought. For sure, there are interesting questions of that kind to be explored. But I think, disappointing though it may be, my inclination is to say the same as I said in response to the earlier question, that actually we ought perhaps to resist the temptation of assimilating things too readily. I think that different kinds of questions are being raised at that point about the nature of human intelligence or about the nature of human self-consciousness or whatever. And certainly specifically as far as arithmetic is concerned, there's no reason to suppose that the argument can be reiterated at a higher level. In fact, as far as the Lucas Penrose argument is concerned, it leaves open the possibility that human beings can just get it right, can hit the sweet spot, that human beings do have the ability to discriminate between the true and the false within arithmetic. That's a possibility that's left open. It's just that if we do, we don't do it by means of some finite stock of basic principles. But if we're hitting the sweet spot, and as I say, the Lucas Penrose argument leaves open that possibility, then the question of whether some higher intelligence might react to our limitations in the same way that we react to the limitations of a computer just doesn't arise, because we aren't limited. We've got it right. We've arrived at exactly where we want to arrive at.
Okay. Well, actually, just I'm going to give us another minute. Do we have a question in Hamburg? Last one from Hamburg.
Both more questions. Thank you.
Sorry?
Sorry, there's one more. Sorry.
All right. We'll have that.
Yep. So I'd like to know what or if Penrose Lucas mentioned or talked about metaprogramming, which was already present at the time that their work was released. Programming being, roughly speaking, the ability of programs to alter themselves. Why is that not as sufficient?
That's an excellent question. This relates back to the first way of trying to resist their argument and looking at ways in which they may have underestimated what computers can do. And it is a very natural proposal to say, well, look, maybe what's required here is to program computers in such a way that they're not just operating with some finite stock of basic principles that they're using to prove more sophisticated results, but they're also self-regulating in various ways, and that periodically it can kind of update its own software. And I think we do have to take that possibility seriously. Lucas and Penrose themselves are not unaware of this kind of thing, and their concern about this is, I mean, roughly speaking, what they're going to say is that when all's said and done, even if you build into the computer a kind of self-regulation of that kind, the fact of the matter is that you're programming it, you're giving it some basic principles to work with, and it may be that it's not just a simple set of axioms in the way that we were originally envisaging, but it's going to be a simple set of principles or procedures for periodically supplementing those axioms. And then the worry is that some variation of Gödel's theorem will kick in again, or maybe Gödel's theorem itself will kick in again. And I think, I mean, this is hand-waving on my part, but I think this is one of those cases where you have to say that the devil is in the details. We just have to look and see what exactly is being proposed, and whether what's being proposed is straightforwardly still vulnerable to Gödel's theorem or not. But certainly they thought that there were reasons in principle why they could foresee that whatever was proposed would be vulnerable to Gödel's theorem.
Okay. Well, thank you. I think we will stop there because it's just after 1:15. So first of all, thank you, Hamburg, for all those questions. It was great tonight. Next time we hope we'll be on the screen. I think we will be on the screen because a couple of us will be in Hamburg and on the big screen here. But next time, the date is on your program in May. We tend to be in third week, if that means anything to you, of Trinity of each term. But we always put the dates on the back of the program, and that will be Science in the Brain. And I want to thank our speakers for great talks and for keeping to time, because it really meant that we could have good discussion and enough time for tea. And thank the audience for such great questions, and thank us all. So,
thank you from Hamburg.
Goodbye, Hamburg. We'll see you next time.